this quiz, we're going to continue to look at chemical reactions. And to start off, the question is asking, what is the difference between a coefficient and a subscript in a balanced chemical reaction? And if these terms seemed a little unknown at the start of the quiz, that is okay, but very, very important to understand what they're referring to mathematically. And so let's look at our example. The subscripts mean the number within the molecule, and so this ends up being the little number that is sort of at the foot of a molecule, a foot of a letter. And a coefficient is the number of molecules, and this is the big number in the front. And in other words, if we have 3 CO2, this means that 3 is the coefficient, that's the big number in front, and this little 2 is the subscript, so that's the little one that's down in the corner. And these have very, very different meanings, because if we say 3 CO2, what we're looking at is a picture like this. So here are 3 different molecules of carbon dioxide, which is what is told to us if we say 3 CO2 in this way, right? If 3 CO2 appears in a chemical reaction, we do want to be thinking about making 3 different carbon dioxides. And that's what this is, right? It's 3 molecules of carbon dioxide, 3 copies of carbon dioxide, CO2. And each of these has 1 carbon and 2 oxygens. If a subscript is not given, like on carbon, then the value is 1. And if it's given, then that's its value. So when we have CO2, that's 1 carbon in black, 2 oxygens in red for each of these 3 identical CO2s. And that's a really important starting point for working with chemical reactions. Next, we want to say, well, what is the number of each atom in the following reaction, and is it balanced? We've talked about balancing chemical reactions, where what we want to make sure is that the number of atoms on the reactant side is equal to the number of atoms on the product side. So let's take a look, right? If we look at hydrogen, we have 2 atoms on the reactant side. There are 2 atoms of hydrogen in each of these 1 H2 molecules, but there's only 1 HCl on the product side, which is only 1 atom of hydrogen. If we look at the chlorine, there's 2 atoms on the reactant side, but again, just 1 on the product side. So what does this tell us? Well, this tells us this is not balanced. We absolutely must have the same number of atoms of every type of molecule on each side, and we can change that by changing the coefficients, the big number in front. This is not balanced, and therefore we need to balance it before we can use it in any calculations. So if it's not balanced, let's now balance it and state if it is balanced, why balancing might not be needed, right? So we already determined that this is not balanced, and how are we supposed to fix that? So let's look at each atom in turn. So let's first look at the hydrogens. There's 2 on the reactant side, 1 on the product side. So as we look at this, we want to be thinking, well, how can we fix that with what we have here, right? And so I would think, like, maybe we can double the HCl. Maybe this makes 2 hydrochloric acids on the product side. And let's give that a try. Let's stick a 2 in the balanced chemical reaction, or our working reaction that we hope is going to get towards balanced, and let's see what we get. Now, hydrogen is balanced. We have 2 on the reactant side, and because we have 2 copies of HCl, each of which has a single hydrogen, now the hydrogen is balanced too. What about the chlorine, though? If we look at this, now actually there are 2 chlorines on the reactant side and 2 chlorines on the product side. So the chlorine is balanced as well, and that means that this is a balanced chemical reaction, and we're pretty much done. So now we move on to part D, which says, well, let's try to do some math. Let's try to do a calculation based on this balanced chemical reaction. So we've made the balanced chemical reaction here in the previous parts, and now we want to calculate the mass in grams of hydrochloric acid produced from 10 grams exactly of chlorine in excess hydrogen. So let's start with what we know, right? This is where we always want to anchor one of our calculations. Start with what we know, 10 grams of Cl2. And the path that we want to take is we want to recognize that we need to turn chlorine in grams into chlorine in moles, because moles is the number of chemicals that we deal with, right? It's a number like a dozen. It's a large number, but that's what captures the numerical information. And that's really what this balanced chemical reaction is saying, is that 1 molecule of hydrogen, 1 molecule of chlorine is going to make 2 molecules of HCl. So the first thing we need to do is we need to convert this grams into moles. And we do that with the molar mass. We calculate this by saying, well, there's 2 chlorines. Each chlorine has a molar mass equal to its atomic mass from the periodic table. So we get chlorine's atomic mass, we double it, and that gets us 70.90 grams per mole for chlorine, and we apply the dimensional analysis that we've been working on so far. After this, we want to use the balanced chemical reaction because it tells us that 1 mole of chlorine is actually going to make 2 moles of hydrochloric acid. And so that's what we want to apply, right? Moles of chlorine, we want to cancel with moles of chlorine and make it into moles of hydrochloric acid. Now, our unit, if we were to evaluate this expression, would be in terms of moles of hydrochloric acid. But we want to go all the way to grams of hydrochloric acid, and so therefore we need to multiply by its molar mass as well, right? Moles is a great thing to know, but easier to measure in a lab is grams, easier just to measure in general. And so grams of hydrochloric acid using that molar mass is our last step here. That gets us to an evaluated value of 10.3 grams of hydrochloric acid, and this is our final answer. To review, again, this dimensional analysis approach, we start with what we know, grams of chlorine. We want to cancel that out using the molar mass to convert first to moles of chlorine. Now we want to convert to moles of HCl using the balanced chemical reaction. That gets rid of our moles of chlorine. And then finally we want to move from moles of hydrochloric acid to grams of hydrochloric acid. And we set up the molar mass of HCl to do that conversion. And we end up with 10.3 grams, 3 sig figs. That's based on our original 10.0 grams of chlorine, which is also a 3 sig fig value.